When on February 10th in 2016 you were switching on your news program and were waiting for the latest update on the American elections or domestic policies in England or other countries, you were up for a surprise. The news programs opened with the announcement that gravitational waves were detected by LIGO for the first time, confirming yet another prediction of Einstein's theory. You had to wait a bit until the politics finally came. And it is my pleasure to introduce one of the key researchers behind this momentous discovery of science that made it to the newspaper headlines on February 2016. Gabriela González obtained her PhD in 1995 in upstate New York at Syracuse University. She then moved to the Massachusetts Institute of Technology, which, together with Caltech, runs the LIGO laboratory. She there joined LIGO. A few years afterwards, she moved on to Penn State University to become a professor there. And in 2001, she moved to Louisiana State University in Baton Rouge, where she has been since and is now a full professor. Her awards and services to the community are too numerous to go through here in their entirety. A selection includes the following. She was awarded the title Pioneer of Science in Science at the World Science Festival in New York in 2016. She's a fellow of the American Physical Society and the Institute of Physics, was awarded the Edward Boucher Award by the American Physical Society. And together with the LIGO Scientific Collaboration, or LSC for short, she received the Gruber Cosmology Prize and the Breakthrough Prize in Fundamental Physics for the detection of gravitational waves. She served on the NASA National Advisory Council, on the Program Prioritization Panel of the National Academy of Science for the Astro 2010 Decadal Survey, known to many of us simply as the Decadal. She held numerous positions in the LIGO Scientific Collaboration, but most importantly, from 2011 to 2016, she was a spokesperson of the LIGO Scientific Collaboration. This implies that she ran mostly the organization up to the time when the breakthrough was made. The event was discovered in September 2015, and this, of course, is a momentous achievement. It becomes even more momentous if you bear in mind that for all these years, until September 2015, there was no certainty that this would work out. There was the nagging doubt, my God, is it really going to work out? It has worked out. Thank you for all your efforts on this, and let us welcome, with a warm round of applause, Gabriela González.
Thank you. It's a great honor to be here. It's celebrating Stephen Hawking's 75th birthday, and even more talking about black holes, since what we discovered on September 14 was gravitational waves from black holes. And I'm very glad to be talking here on behalf of the LIGO Scientific Collaboration and the Virgo Collaboration. This is a great number of minds, a great number of people, international, in many different countries that work together and keep working together to do this. Now, it all started long ago. In 1915, Einstein's theory, as Brian told us, was revolutionary in creating a new concept of space-time. Space-time was not this absolute grid that Newton talked and we tend to think about. It's a grid, a three-dimensional grid with clocks in there that is dynamic. It gets warped by all masses. But not only that, if the masses wiggle, then those distortions travel at the speed of light, and those are the gravitational waves. Einstein published this theory of gravity in 1915, and in 1916, with very simple approximations, it's not an exact solution like Maxwell's solutions, but with very simple approximations, he concluded that gravitational waves existed. However, he also calculated that they would be so small that there would be no point in looking for those to test his theory. He was wrong. In 1915, there was also the first exact solution to Einstein's equations, and that was a solution that was later realized it was describing a black hole. But at the time, it was simply a beautiful solution if you assumed spherical symmetry. And it said that if there is enough mass, then the space-time is so warped, that not only there is a singularity at the very center, but there is a horizon from which nothing can escape. And that's why Wheeler in the 60s popularized the term black hole, although black holes as stars from which light could not escape had been theorized much, much before that. But for many years, this was just a weird mathematical fact, a consequence of Einstein's theory. Nature would never produce things so strange as that. Nature produces stars and galaxies, but black holes, that would not quite be the case. There were many scientists, including Wheeler, that in the 60s and 50s and 60s and 70s began thinking more seriously about that, and that was, including Stephen Hawking, from which I have several references. Now, we know since then that black holes exist. We do know because we have experimental evidence. It took a long time to come by, but we do have very serious experimental evidence. We do know that, for example, if we look at the center of our galaxy and we trace the stars that go around, we can use Newton's laws to deduce that there is something at the center, something that's almost 4 million times the mass of the sun in that very small space in between the stars. That is a black hole. We now believe that almost every galaxy has at the center a black hole. And some galaxies have black holes that are so active that they emit very, very strong radiation. We call these active galactic nuclei. And that's a picture, a radio picture of a galaxy that we think contains a black hole in there. So this is very strong evidence of black holes, very, very massive black holes at the center of galaxies. We also have some evidence of small black holes. And we do know, can you go back one, please? We do know that black holes start very small. And they start small because astrophysics tells us that they start from the explosion of supernovas. But in those cases, most of that matter comes away in the explosion. And we also think that black holes are formed when we have two neutron stars that are orbiting around each other. And according to Einstein's equations, not Newton's equations, they get closer and closer to each other because there are gravitational waves carrying away the energy. And when they merge, when they get close, so close that they merge into a single star, that is not a star. That is a black hole. And in that process, both in the supernova explosion and in the merging neutron stars, we would see emission of gravitational waves, not just the black hole being born. Now, we haven't seen proof that the supernova leaves behind the black hole or that neutron stars. We have not seen an actual merger of neutron stars that has a black hole. But we do know about small black holes because some black holes are in orbit around another regular star. And then the emission of light from this star, the black hole does not emit light, but the star does, we can tell that there is a black hole there. And we can measure the mass from knowing the orbit. We can also see, in some cases, the emission of X-rays from the matter falling into the black hole. And from these X-ray studies, we have a small catalog, because there's only a few known, But we have a small catalog of masses of black holes that are small. They were all less than 20 solar masses or so, because again, they start small. So now black holes is not a mathematical weirdness, it's now an astrophysical matter. And as I was saying before, Stephen Hawking was interested in black holes even from the very early on, when not many people, certainly not many astronomers, believed in black holes. He has some papers from the 70s of black holes in general relativity, and not only that, for gravitational radiation from colliding black holes, how much matter can be emitted from the collision of black holes. Evidence for black holes in binary star systems. How could we find black holes if we looked at binary systems when one of those was a star? That's how we found them. That's how we found the small ones afterwards. Now, only about 10 years ago, we could really solve exactly Einstein's equations, but on a computer. So this is what happens if you have two black holes. You can draw the space-time near the black holes, and you see the two throats, but you can also draw the distortion of space-time far away from the black hole. For example, on Earth, if these two black holes were 1 billion light years away. So this is 5 milliseconds before merger. We see the space-time getting really weird as the black holes are about to merge. Notice the distortion of space-time started like a sine wave, but then it grew in amplitude and frequency. And at the merger, we now have only one horizon, a perfectly spherical, rotating black hole, but very simple, very quiet, with the gravitational waves carrying away all that information about what happened. And notice that the information that we could receive here on Earth, if we could detect these gravitational waves, is relatively simple. It's a sine wave that increases in amplitude and frequency until the two black holes merge, and then we have a simple ring down. So now we know what to look for. How do we look for these? That's another matter. Those distortions are very, very small. We could think about using an interferometer. An interferometer measures changes in distance, changes in space-time that are different in the two sides, in the two arms of the interferometer. We can see the interference of the light waves coming out, the laser light. If the two lengths are exactly the same, we see no light at the output because the two waves cancel each other. But if there is a gravitational wave going through, then these two distances would change. One would shrink, the other would lengthen, and then we would see on a photodiode more light, less light, and that would tell us that there is a gravitational wave going through. That's the principle. The practice, however, it's a lot more complicated. Because the principle, that calculation I showed you before, and even simpler calculations, tells you that the distortion you're looking for is very, very, very small. If you had, for example, two neutron stars, well, in our galaxy, they would produce a very strong gravitational wave, but that only happens once every 10,000 years or so. And even for physicists, that's too long to wait. So let's think about perhaps an instrument that looks farther away. Our galaxy lives in the Virgo cluster, so let's think about coalescence of neutron stars in the Virgo cluster. That also is not so common. It happens once every 50 years, about as often as a supernova in our galaxy, but that's something to look for. How strong would be that gravitational wave? It's about the same amplitude as the gravitational waves from two black holes that are much farther away, because black holes emit stronger gravitational waves. But they're still very small. The distortions, if we had an interferometer where the Earth was in the center and the sun was at the other end, and then we have the same distance on the other side, then the distortion we're looking for is a part in 10 to the 21, which means an atomic diameter. Measuring the distance between the Earth and the Sun. And Einstein tells us that for smaller distances, the change is proportionally smaller. So how could we measure this on Earth with interferometers? It sounded impossible, except to a few scientists, not that many, a few scientists that in the 70s said, well, if we make this long enough and precise enough, we could measure this. So they proposed to the National Science Foundation, and they only convinced the National Science Foundation in around the 90s. These were Ron Driver, Kip Thorne, and Ray Weiss. Ron Driver sadly passed away very recently, to build 2 detectors in the US that were 4 kilometers long on the side, and I don't have to translate that into miles, being here in the EU, but I will, being in the UK. These are 2.6 miles. And the idea is that we have a laser at the center that travels 4 kilometers, meets mirrors at the ends, brings back, and then we make them interfere at the center. Now, if we have 4 kilometers instead of the distance between the Sun and the Earth, we have to be a lot more precise, because the change in distance is still a part in 10 to the 21. So how much more precise? Well, that's smaller than an atomic diameter for sure. It's smaller than a proton. It's a part in 1,000 of a proton. And that sensitivity was achieved. It took a while, and it was achieved in 2 different detectors, not just in LIGO Livingston, which is close to Louisiana State University where I teach, but also in Hanford Observatory. Why do we have 2? Because these signals are so tiny that if we wanted to convince ourselves, let alone the rest of the world, we would need to see it in 2 different detectors at about the same time. How did we do this? How did we achieve such amazing precision? Well, first of all, we used a lot of technology, which means a lot of people, engineers, technicians, physicists, inventing the technologies and then installing them. It's not just a simple interferometer, it's a much more complicated optical system that I will not put the schematics here, but the lasers travel in vacuum tubes, 4 kilometers of vacuum tubes. The mirrors are not simple mirrors bolted down to an optical table. They are big mirrors that are hanging from glass fibers, from another mirror that are hanging from blades, that are hanging from blades, and all of that is to isolate from the seismic noise, from the wiggling of the ground that wants to move the mirrors. And that is not enough. We have those big quadruple pendulums hanging down from an active seismic isolation system where we have layers of metal where we measure the relative motion and we cancel it. And all of that is inside vacuum chambers. And the laser that we use is a laser that is a high-power laser that has lots and lots of photons to allow us to resolve better the arrival of the photons fighting the quantum noise in the light. So this is a very complicated experiment. It took 2 generations of technology. We had initial LIGO detectors running between 2005 and 2010. We didn't see anything. We didn't see gravitational waves. You probably would have noticed if we did, you would have heard. But we had then a second generation of technology, a more advanced technology. We call these the advanced LIGO detectors. This was at the Harvard level already an international collaboration. It wasn't just a National Science Foundation. It was the Max Planck Institute with the lasers. It was the STFC Council here in the UK with the suspension systems. We put it all together, and we are not done yet. We can make a detector that is as sensitive as a part in 10 to the 23, not just 21. We can see farther away than we did before. But in 2015, we were already 3-4 times better than we had ever been before. Not the 10 times better that we wanted to be, but halfway there. Less than halfway there. And we say, let's take data for a few months to see how everything works. We won't see anything because we don't yet have enough sensitivity to see these neutron stars, but let's take data anyway. And as you know, on September 14 of 2015, we saw this. This was amazing. It was such a big surprise that even in the beginning, we didn't think it was real. We thought somebody was playing with us. It was nature. What you see here in orange is the data from the Hanford Observatory, and in blue, the data from the Livingston Observatory. So this is a light on the photodiodes that I showed you before. You always see some light because there's always some noise in there. That noise, if you put it as a fraction of distance, you can see the scale on the left side is about 10 to the minus 21. A part in 10 to the 22 is about the noise that we have. But then you see that in the two detectors, 3,000 kilometers away, you see what appears like a sine wave that goes together, although we had to shift the data from the Hanford detector 7 milliseconds to make it match the one in the Livingston detector. But it is what we expected from a coalescence of two stars, a sine wave that grows larger in amplitude, larger in frequency, and then it settles down. And if you look at the time scale, this is a small fraction of a second. These frequencies are around 100 to 100 hertz. Those frequencies are telling us that the two stars are huge. These are not just stars. These are not neutron stars. These were black holes. Black holes, each one about 30 solar masses. Huge black holes for what we call stellar mass black holes. This was just incredible. It took us months to convince ourselves that there was nothing wrong, there was no room for error in here, but it was true. On February 11, 2016, last year, we stood up and we said, we did it. Now, we is a lot of people. And this is the people working today in the LIGO scientific collaboration. There's also the people in the LIGO, in the Virgo collaboration, and we work together analyzing the data. And there is also the people who have worked on this in the past. So this is a lot of people, and I just want you to notice, in case you haven't already, that University of Cambridge is right there too. So this is a very big international collaboration that I had the honor to lead, especially at the time of the announcement. Now, that's not the only thing we did. As I told you, we were planning to take data for a few months, and this discovery on September 14 was right at the beginning. We hadn't quite begun to take data 24/7 like we do for an observing run, but we took data for 4 months, until January of 2016. And then, as I told you, on September 14, we saw this signal from the coalescence of two black holes. And on December 26, although it was December 25 in the US at the time we saw this, so it was still our Christmas gift, we saw another coalescence. Not as big, so I cannot show you that nice wiggling signal I showed you before, because it wasn't as big, because it was produced by smaller black holes. But it was still much, way above our noise for us to identify it. And there was even a third, which is in shaded form there, that we call a candidate. That was on October 12, 2015, which is consistent with a coalescence of two black holes with masses in between the other two, but we're not completely sure. It's a smaller magnitude, so it's not as conclusive as the other two. I didn't tell you about the distances. From the amplitude of that signal that we saw on September 14, we could tell not only that the masses were 29 and 36 solar masses, which together made a black hole of 62 solar masses. And now for those people who like arithmetic, they're probably saying, she made a mistake. 29 plus 36 is not 62. And that's because there were 3 solar masses of energy emitted in the gravitational waves. Remember that formula E equal mc squared? The m in the energy was 3 solar masses. That's more than the visible light in all those beautiful pictures that Brian showed us before, for that fraction of a second. But in gravitational waves, which are dark. But from the amplitude, we can also tell how far away this system was. And that first system that we saw was 1.3 billion light years away. That's very far away, although when they were emitted, certainly Einstein was not on Earth. Human civilization was not on Earth. Those multicellular organisms in that beautiful Earth chart that Brian showed, they were just getting formed. It was in the middle of that huge chunk of Earth's life. So that's when the black holes merged that long ago. That second candidate, if it was real, would have been 2 billion light years away, so that's why it made them smaller. This one was 1 billion light years away, but they were smaller masses, and that's why they were smaller. So we have evidence now. It wasn't just a one-time thing. We had 2 observations. What have we been doing since then? Well, a lot. Let me tell you more about that. But before that, let me make you hear these gravitational waves, the 2 first gravitational waves. One was very short, a fraction of a second. That's a September one. The December one was longer, was almost a second long. And we can plot here a time frequency diagram that shows the evolution. And I will make you hear first these 2 notes from the actual output of the detector with minimal filtering, like I showed you the time signals before. Oh, can you go back and play it? That's a long one. This is the short one. That's a long one. This is a short one. Now, these are actually what we call the natural pitch. To make them nicer, just like astronomers use different colors to represent infrared light and ultraviolet, which we cannot really see, but we like to put them in pictures. With us, for the sound, we increased the pitch. We added 400 hertz to the sound. And now they are more musical. And this is, if you have heard this before in YouTube, this is probably what you heard. Long one. And short one. But now you know the truth. This is not how they actually sound. The sound is 100 to 200 hertz. It's a lot lower. We still love them. We dance to this music. Now, what have we been doing since then? Well, I told you that the detectors are not yet at the sensitivity that we want them to be, so we still have some work to do. In January 2000, in the run in 2015, we saw 2 detections. We call that the first observing run, 01. We had a range to binary neutron star coalescences, these that would produce not just gravitational waves, but they could also produce, we expect them to produce electromagnetic waves. The range that we have for those was between 65 and 80 megaparsecs. We worked on the detectors. We made one a bit better, one a bit worse. We are trading techniques to make them both just as well as we want them. And in the second observing run that started on November 30th last year, we plan to take data until August or so. We had a range between 60 and 100 megaparsecs. So a bit better, at least in one of the detectors. And we already saw one gravitational wave on January 4th, just after coming back of the holiday break. These gravitational waves always seem to come when we are not quite ready at the beginning of the run, on the December break, although we didn't take a break, and we were very glad we didn't take a holiday break, just after the first break. We are still taking data. We will until August. A third detector is about to join us any minute, the Virgo detector from Italy, and then we will have 3 detectors taking data. Then we will take another break to make them better. In 03, we have a target of between 120 and 170 megaparsecs range. We expect that if we have 150 megaparsecs and quite a few months of coincident data, we might begin seeing coalescence of neutron stars. That would be great. Not just black holes, not just the dark side of the universe, but the bright side of the universe. And of course, we'll keep going until we get better and better. The technology that we have today can allow us to see 200 megaparsecs away for binary neutron star systems. Of course, we already know how to do things better and better if we have enough money and time, which is not there yet. But this is not the only story, because 2 detectors cannot quite let you know where the gravitational waves come from. With 3, you can triangulate, but you still have a lot of uncertainty. So you need a network of detectors, and that's what we will have with the Virgo detector. Now, let me show you graphically what we have done. I told you that from X-ray studies, we knew quite a few of stellar mass black holes. This is what we know now from gravitational wave observations. We know of bigger black holes as well as the smaller ones that we expected, and we see quite a few more. And we also saw pairs of black holes that we had never seen before. 2 black holes merging into one. That was a first. We knew it could happen, but it's just like the solution, the mathematical solution of black holes. You know it exists, but does it exist for real? We knew binary black holes should be out there, but now we know for sure. So this is the catalog of black holes that we are building, but of course we plan to see a lot more of other signals. Rotating stars in our galaxy would produce gravitational waves, exploding supernova in our galaxies, neutron stars, merging neutron stars, and of course, the unexpected. And this is all being looked for by a network of gravitational wave detectors, not just the 2 LIGO detectors in the US, but the Virgo detector in Europe. We are working together. Like I told you, Virgo is about to join the second observing run and the future ones. There's an observatory in Japan called Kagra that is probably going to be running around 2018, 19. We are always a bit optimistic, but it's going to be only 2, 3, a few years until we have another Japanese detector with the same sensitivity. And there is an observatory approved for construction in India that would host another LIGO detector. We call that LIGO India, and that would begin working 2024 or so. So the next decade, it's going to be seeing not just more discoveries with LIGO and Virgo detectors, but more discoveries with this whole network. More detectors, more discoveries. And all these detectors are sensitive to a relatively small frequency band. We like that band because we can hear the gravitational waves, but gravitational waves detected in that band are only from small stars, like neutron stars or small black holes. But there are many gravitational waves produced at many other frequencies. Larger black holes, like the ones at the center of the galaxies, would produce gravitational waves of periods of minutes to hours instead of tens of milliseconds. So those we will detect with a space project pioneered by the European Space Agency and now joined by NASA called LISA. And if we want to see gravitational waves from supermassive black holes, or perhaps the rumble of the early universe, then we can see that with an interferometer in which we have beams traveling the galaxy. How you can do that? Well, we don't do that. Nature did that with stars that emit radio beams. We call them pulsars. And if we time those radio beams from different pulsars and measure the different phases, the correlation in the phases, then what we have is an interferometer of galactic scale. This is called pulsar timing, and this would allow us to see gravitational waves with periods of years. And this is working. I expect a discovery from this in the next several years. In fact, it could have happened already, but we don't know yet. And if we want to see gravitational waves from the very early universe, in that quark gluon plasma, the very beginning of the universe, there were no stars, there were no atoms, but there were gravitational waves because matter was wiggling around. So if we want to see those gravitational waves, those are the most difficult ones to see. So we rely, the best bet to do that is on measuring the polarization of the cosmic microwave background of that beautiful map that Brian showed us before. So we can map the history of the universe with gravitational waves, not just with visible light. And this is all coming to you. Now, going back to black holes were these weird mathematical objects in the very beginning. Lots of physicists worked on this, including our birthday person, Stephen Hawking, and we convinced that they were real. We discovered them, not just with evidence from visible light, but with gravitational waves now. But there's a lot more about black holes that we don't know. And there's a lot about black holes that we know from Stephen Hawking that we have not seen observations yet, but I'm surely hoping there would be someday. And that is that black holes, those black holes that were left after, for example, the merging of our systems, the systems that we observed, according to Einstein, they would stay there forever, perhaps rotating, but forever. According to Stephen Hawking, they would not because they evaporate. If you use simple laws of quantum mechanics, black holes are not eternal. So that's actually, to me, an optimistic thought, because again, it tells us about lots of other things that are out there to prove and to discover. And this is one that I would really love to see evidence for, not with LIGO, but from LIGO and from the LIGO collaboration, we are here to say happy birthday and thanks for the work of all your life. Thank you.